Alright, hi. Our presentation is on the MRI and the physics behind it. And I'm Pam. Victoria's in this too, and Andrea is as well. So the MRI, it uses strong magnetic fields to create a detailed cross-sectional image of the body. So it basically takes like slices, or like takes images of like slices of like your head. It allows to look into the body non-invasively, and no magnetic object should ever be near the MRI because the MRI is basically a massive magnet in itself. So it's also really important to stay still, like when getting the MRI, because like I said, it's taking slices of your body, so just making any movement would just basically blur the image. The scanner contains two powerful magnets and allows for water molecules to align according to magnetic field. And the fMRI measures brain activity and checks for structural abnormalities. So whenever there's like any brain injuries, you would probably look into getting an MRI. This is a video.
Here's the MRI scanner. If you need to have an MRI scan, you'll be brought into a room much like this. You lie on the table, you go into the middle, you come back out again, and you get changed. It usually takes about 15 to 20 minutes to have a scan. I'll show you the table going in. As you can see, there's plenty of room and it's well lit. Once it's finished, bring you back out again. Obviously you have to imagine the person. And the table comes down. And your scan's complete. It's as simple as that.
The history and the application of the MRI. So the phenomenon of the MRI was discovered in 1947 by Felix Bloch and Edward Mills Purcell. It took a while because it was just a phenomenon that was discovered, and not till Paul Latimer and Peter Mansfield, they were the first to obtain the actual images for like clinical use, like of the images from the MRI, and then they were recognized for it 56 years later after the discovery. Application-wise, what they were using it as like clinically, it doesn't harm, and so it gives like a safe way of seeing into soft tissues such as the brain, heart, and it's a way for us to find tumors in many organs without having to like actually like surgically go in and look for them. So yeah.
Okay. So what happens to an MRI in terms of physics? So what happens is that obviously a moving charged electric particle will align to a magnetic field and causes a magnetic field. And the biggest amount of electric charges that we have in our body are hydrogen atoms. Okay. The biggest reservoir of hydrogen atoms are in our body by means of water. And this is really important because water is the biggest source of protons in the body right above fat. And its direction is always random, but when it aligns with the really large magnetic field of the MRI, it'll either align with the magnetic field or directly against the magnetic field. And that's dependent on whether those protons have a lot of energy or they have a low amount of energy. So the MRI is able to use those good images by the fact of the difference of energy that the fat or the water releases in that regard. Next slide, please. So if you want to go more in depth about the MRI, you have to look at how it actually works. So what happens is that you have the protons going in different directions in the body by means of water or in fat. And then when you align it with the magnetic field, it'll either be parallel to the magnetic field or anti-parallel to the magnetic field. If it's anti-parallel to the magnetic field, then it has a lot of energy, whereas when it's parallel to the magnetic field, it has a lot less energy. Now what happens when you add a radio frequency to these protons? They suddenly all go towards the anti-parallel position because obviously they gain a lot more energy from this radio frequency. But where the difference comes in is how the energy is released by means of T1 and T2 relaxation. In T1 relaxation, the initial energy is released, and when it comes in terms to fat and water, fat releases a majority of its energy in the T1 relaxation period. In comparison, the T2 relaxation period is another, per se, relaxation of energy, and this is what usually happens with water. Because they release energy at different times, the MRI takes into account those different times in which it releases energy and is able to create a contrast within those images. So as a result, it's because of the whole longitudinal magnetization. Because if it lines up with the magnetic field, the MRI can't really create a picture. But when you add the radio frequency to the field, then it goes from a vector that's like this to something that's horizontal, which is perpendicular to the field, and it's much easier to detect. Once you remove the radio frequency signals, that's when you have the T1 and T2 relaxation, and that's how you're able to create a contrast within those images. So, as stated again, once there's that loss of energy, that's what helps create the contrast between the lipids and the waters within the body.
Okay, so now over to the major components of an MRI, as this picture shows. So there's 4 major components. The first is a primary magnet, and this refers to the strength of the permanent field of the MRI, which is usually about 1.5 to 3 Tesla. And in the primary magnet, you have the hydrogen atoms, which are lying parallel or anti-parallel to that primary field. And this whole process is known as longitudinal magnetization. The gradient magnet is the second concept, which the gradient magnet produces a secondary magnetic field in addition to the primary magnetic field produced by the primary magnet, which would be symbolized by the color purple here. The gradient magnet is located within the bore of the primary magnet. And also, the gradient magnets are arranged in opposition, and this is so that negative and positive poles can be created, and this allows the MRI the capacity to produce images along 3 axes, the X, the Y, and the Z axes. The radio frequency, or RF coils, is the third component, and it's used for transmitting radio frequencies and also for receiving signals in the MRI. As you see in this picture, the RF coils are the green parts, and there's also like an RF signal box, which it functions to receive the signals in the MRI. The radio frequency coils come in various shapes in order to accommodate the different body parts. Since they're up here, these would be there to accommodate the head, for example, but also the shoulders, the knees, legs, etc. The radio frequency coils are also help to transmit the secondary magnetic field, and they allow some low energy parallel protons to flip to a higher energy state. And after the RF pulse, or the radio frequency pulse, several of these protons flip back to a low energy state, and this transmits energy to the surroundings, so it helps the MRI ultimately create a picture. The computer system, the fourth component, it receives the radio frequency signal, and then it produces a digital conversion, and it's sent, the digital signal is sent to a processor for what's called the FT transformation. It's like a mathematical formula called the Fourier formula, complicated formula, just make sure that this signal ultimately gets created into a picture that you see on the monitor.
No, I have to do it. Okay.
Okay, so an important concept of an MRI is the use of solenoids. Solenoids produce very strong magnetic fields that can be turned on or off by a switch. So this is in contrast to a permanent magnet, which you can't just turn it on or off that way. A solenoid, what it is, it's an electrical device, and it's just pretty much essentially a long wire wound into, quote, a succession of closely spaced loops with the geometry of a helix. It's also known as an electromagnet because when it's carrying a current, it produces an intense and pretty much nearly uniform magnetic field inside the coils. And each solenoid's loop carries a current in the same direction. This means that magnetic force inside is attractive, so that means the loops are held closely together. And MRI machines use solenoids that are very large, so that's why they can produce very powerful magnetic fields, 1 or 2 Tesla in power. So here are just the different parts of an MRI machine. If you see here the superconducting solenoid, it's pointing to this area right here, and that's where the solenoids are found in an MRI machine. Here's an example, a basic example of a solenoid. So in this case, it produces a magnetic field of 1.5 Tesla. You see that in the coils, it would produce an intense, nearly uniform magnetic field. So this is a quick summary of the physics behind how an MRI works. It talks about the different components of an MRI as well, and how the hydrogen protons align, and how they release energy in the process.
A greater proportion of the hydrogen protons align in the direction parallel to the primary magnetic field or low energy state than align anti-parallel to the primary magnetic field, the high energy state. The net result, called the net magnetic vector, is therefore in the direction of the primary magnetic field. This is orientated in the patient's long or z-axis. The protons spin on their axes much like a spinning top. This is called precession. The precession rate is called the Larmor frequency. When protons precess together, this is known as in phase. When protons precess separately, this is known as out of phase. The frequency changes in proportion to the magnetic field. At 1.5 Tesla, this is 63.9 MHz. The gradient coils generate secondary magnetic fields over the primary field. They are located within the bore of the primary magnet. They are arranged in opposition to each other to produce positive and negative poles. The arrangement of these gradient coils gives MRI the capacity to image directionally along the Z, X and Y axis. There are 3 gradient coils which are named according to the axis along which they act. Gradient magnets alter the strength of the primary magnetic field, thereby changing the precession frequencies between slices. This can then be used for slice selection and localization in the X, Y and Z axes, called spatial encoding, of MR images. The Z gradient runs along the long axis to produce axial images, the Y gradient runs along the vertical axis to produce coronal images, and the X gradient runs along the horizontal axis to produce sagittal images. The radio frequency or RF coils are used for transmitting the radio frequency or RF pulse and receiving signals in MRI. They come in many designs altered to best suit each body part, all aiming to improve signal-to-noise ratios to produce the best possible diagnostic images.
So there are some possible dangers associated with an MRI and even the room where an MRI machine is found. Because you have solenoids which produce a very strong magnetic field, then metallic objects in the room can be pulled into the bore of the magnet. It has caused various complications. People with artificial pacemakers, if they have what are called magnetic reed switches, which this is for a doctor to place to change the operating mode of the pacemaker without surgery, and they do this by just placing a magnet at a certain location on their chest. But if you have magnetic switches, then you don't want to go anywhere near an operating MRI. There's different contrasting agents that are used for an MRI in order to see differences and in order to see images more clearly. For example, the gadolinium contrast medium is a common one. It's used in like about 1 in every 3 MRI scans. It's injected into the person's body, and it helps improve the clarity of images, for example, inflammation or brain tumors if there are any, certain organs are seen more clearly, etc. So you can diagnose the patient more accurately. So what this gadolinium agent is made out of is an arrangement of atoms that's held together by chemical bonds. The chemical bond is between the gadolinium ion and a carrier molecule. And this carrier molecule is also called a chelating agent. And there's different types of chelating agents that are used. But ultimately what its function is to prevent the toxicity of the gadolinium, but still maintaining its contrasting properties. This contrast medium is injected into a vein, into the person's body, and then it's typically within 24 hours, 90% of it is eliminated through the kidneys. But however, it shouldn't be used with pregnant patients or patients that have kidney complications or any allergic reactions. There has been, in one case, a European agency, or various European agencies, suggest not using this contrast agent just because too much of it stays in the body for a longer period of time than it should. But for now, there's not enough research to essentially prove that. Oh, and here you have before the injection of the gadolinium, and here is 20 minutes after the injection, and you see that the tumor is seen much more clearly. It's a white spot up here. What is this? Oh, so we're going to show this video to teach you all how to read different MRI scans.
Let's start with T1 versus T2. Very similar sequences, and people get tripped up a lot with these. So between T1 versus T2, we've got 2 basic rules that differentiate the two. Number 1, within a given sequence, so take T1 for example, water and fat are opposite signal intensities. Number 2, between sequences, T1 versus T2, a given substance, take fat for example, will have opposite signal intensities. This will make sense in a minute. And let's start with T1. Here's our T1 image. How do we recognize T1? Well, in T1, fat is bright, water is dark, and new blood is bright. And this is useful for anatomic details. We can pick up vascular changes and disruption of the blood-brain barrier when we add in contrast. So let's take a look over here at the image. So water, or CSF, is dark, and fat is bright. So areas where there's a lot of myelin, these deep white matter tracts, are going to show up bright, whereas outer cortex is not. This isn't the best image to demonstrate this, but you'll see the differences when we move on to T2. So let's pull up our T2 image. How do we recognize it? Well, everything is flipped. So now fat is dark. These highly myelinated areas here, which are fat, are dark. Water is bright, so look at our CSF right here in the ventricles. It's pretty bright. But flow is dark, and this is called flow void. So where there's fluid moving at a high velocity, so take a blood vessel for example, it's going to be dark, and that's important to remember. What is the sequence useful for? Again, anatomic details, I think T2 is probably a little bit better than T1, especially our CSF spaces here. It's useful at picking up most lesions kind of in general. One area where it can trip up a little bit is when you have lesions or edema really close to CSF spaces, because they'll both be bright. Okay, so let's compare these two. We've got T1 here and T2. So fat is bright on T1, fat is dark on T2. CSF is dark on T1, bright on T2. Got it? Alright, let's move on to
Okay guys, now we're gonna go look inside Victoria's head. Whoa. She literally got an MRI just for this. We're literally the most dedicated group. Wow. There you go. Woo. Good job, Victoria. Thank you for these MRIs. Now we're going to explain them.
Yeah. Okay, so we're going to explain this image. So the reason why the image looks like this is because it's capturing the T2 relaxation. And if you compare the T1 MRI to the T2 MRI, you can say that the contrast is much different. Because in the T2 MRI, the lipids would be seen as a dark color, as you can see in the brain, since the brain is made out of majority of lipids. And then the water would be pictured in a bright white color. In comparison, the T1 image would be the opposite. So the lipids would be really white, and the liquid would be really dark. So the whole point of why you would have a T2 relaxation image in comparison to a T1 relaxation image is to look at lesions in the brain and to kind of like pick those out in the areas. Whereas if it's dark, it's kind of hard to see those lesions because the lesions may happen in areas where there's water. So to kind of differentiate between the different treatments. So when I was going back to the difference between a T1 and a T2 image, these are actual examples. So this is a T1 image, and this is a T2 image, and this is based on T1 or T2 relaxation. So T1 relaxation is when the lipids release a lot of energy, and the T2 relaxation is when the water releases a lot of energy, and that is showcased by which area in the image is much brighter. In the T1 relaxation, the lipids release a lot of energy, and that's why a majority of the brain is really bright. And in the T2 image, the water releases a lot of energy, and that's why those areas are really bright. The reason why they're very contrasting is to help look at different lesions in the brain, which maybe could be confused with other sections of the brain. For example, you can see how the black section of this image is a lot more encompassing than this image. So it could be something else in that area, and that's how you'd be able to diagnose this. But these scans are normal, so you can't really see any signs of hemorrhaging or lesions, but that's how they would look.
So first, what is MR physics really about? What is MRI or imaging really about? Imaging is about contrast. Here's a photo of a slice of the human body. This is of a deceased person. I just want to focus on the differences between fat and muscle here. I know that fat and muscle tissue are different. Fat is yellow, this muscle tissue is red, and I know that intrinsically those two tissues are different. And visually here I have confirmation of that. Why? Because fat and muscle are going to refract light differently into my eye, and that's that visual confirmation that these two structures are different types of molecules. Now I have an MR image. This is of a similar region. Again, I'm going to focus on the fat and the muscle tissue. And again, I just want to emphasize that fat is different from muscle here on this image. They have different grayscale values. But the question is, how does the MRI machine know that fat and muscle tissue are different? So from here, I'm basically going to talk about the sequence of events in MRI. You can't question this sequence. You simply have to know it and understand it. Just like the sky is blue, the sun is yellow, this sequence of events simply is the way it is. So here it goes. Now first, in order to simplify the discussion, we're not going to talk about all the different tissues in the body. We're going to simplify those down into basically fat and water. And within the fat and the water, I'm not going to be talking about all the different molecules and atoms within them. I'm only going to be talking about the hydrogen atoms. Why? Because the MRI machine only sees the hydrogen atoms. It is the hydrogen atoms that are modifiable by the MR machine, and they're the only atoms or structures that actually give signal. They are the atom that's solely responsible for producing all of the images in MRI. So we're talking about fat and water, we're talking about hydrogen atoms. What's the first step? The first step is I take those atoms and I put them in an extremely powerful magnetic field. How powerful are we talking? I'm talking 3 Tesla, meaning about 25,000 times as powerful as the Earth's natural magnetic field. This activates those hydrogen atoms. It puts them in a state where they're now susceptible to forms of energy. So now I'm going to add energy into the system. What type of energy do I use? I use radio frequency energy. Now you might be wondering, well, what the heck is radio frequency energy and why? Again, you can't question the sequence, you simply have to understand it. So what is radio frequency energy? It's a type of energy that exists on the electromagnetic spectrum. It's the same as light, it's the same as sound, it's the same as X-ray. The only difference is the wave that describes radio has a different frequency and wavelength than, say, the wave that describes light. So it's simply energy that exists at a radio frequency and a radio wavelength. So I have these hydrogen atoms. I'm adding radio frequency energy into these hydrogen atoms. After that, I simply wait. I simply wait and see what's going to happen to that energy. Right, as you know, anything that's in a high energy state is going to try to decrease its energy level. So if I add energy into the system is going to release that energy into the surrounding structures. It turns out that the hydrogen atoms in fat release that energy faster than the hydrogen atoms in water. So I try to exploit that difference between fat and water in terms of its ability to release that radio frequency energy. I track that difference and then I assign grayscale values to that difference. So for example, if fat releases that energy faster, I'm going to make fat bright. Right? Water slower, so I'm going to make water dark. I do this for every hydrogen atom throughout the body, and I track its position in 3D space. From those 3D tracking coordinates, I create 2D slices from this data. This 2D slice will have pixels on it, and in each of those pixels, I have a grayscale value that takes into account how much fat and how much water are in each position in 3D space. Now I have an image that I can interpret and make clinical diagnoses from.